The part of physics called mechanics is a huge area of study. Very generally, it involves the study of the motion of objects and the interactions between them, and then how those interactions in turn affect the motions. Let's take a sort of survey of the theory of mechanics. The first thing I want you to understand is that when we say the theory in science, a theory does not mean a guess. The term hypothesis, that means a guess. But in science, the term theory refers to something much more significant, much more important. A scientific theory, that's an explanation of a broad range of events. And it has to make predictions about how systems will behave, predictions that we can test. So if you observe a system and the prediction that the theory makes is supported by what you observe, then the theory is supported. But if the theory makes a prediction that is contradicted by what you observe, then the theory is falsified and we have to throw it out. So for a theory to be useful, it has to make predictions that we can test. If it does that, and those predictions have been repeatedly confirmed, tested over and over again, and confirmed by many different scientists in different parts of the world over many years, then through that process of observation and experiment, that scientific method, then we can call that set of ideas a theory. It's a very prestigious title. In fact, a scientific theory is no more or less than the most well-supported and reliable form of knowledge that we possess. Nothing that you have learned in school about the world is more certain than a scientific theory. And these are some examples that you may be familiar with. Okay, so we know that a theory is a very important set of ideas that's been tested, that's been verified, that's reliable. The theory of mechanics actually takes different forms in what we call different regimes. A regime is a set of conditions that apply to many events. So on this diagram, I have two axes. This represents the size of the system, very large systems up here. We call it the macro scale, consisting of zillions of atoms. So a chicken is a system made of zillions of atoms that exists on the macro scale, macro large. But a small system on the nanoscale here consists of individual molecules or atoms or subatomic particles. So one regime could be the macro regime when systems are large, and the nano regime when systems are small. On the other axis, we have the speed of the systems, how fast the objects are moving. Speed corresponds to the energy that the objects have. So when the speed v is much less than the speed of light, represented by the letter c, speed of light being 2.9979 times 10 to the 8th meters per second, that's approximately 186,000 miles per second. And I'm given the letter c because it's a constant of nature. When your objects are moving at speeds much less than this, that is the low energy regime. But when your objects are moving at very near the speed of light, that is the high energy regime. So we can talk about the theory of mechanics in these four different regimes. When systems are very large and moving slowly, when systems are very small and moving slowly, when systems are very large but moving quickly near the speed of light, and when systems are very small and moving quickly near the speed of light. These are our four different regimes. Let's look at each one. Classical mechanics, our oldest theory of mechanics, was developed by Sir Isaac Newton, an Englishman in the year 1687. In this theory, space and time are separate things. We've got three spatial dimensions, x, y, and z, three directions you can move in, and we also move through time. So here's a billiard ball, an example of an object that you could study in classical mechanics because it's made of zillions of atoms. When I say zillions, remember a good old Avogadro's number. A sample of matter, like this chicken wing here, contains anywhere from 10 to the 21 to 10 to the 23 atoms per every gram of substance. So zillions refers to a number approximately this big. So a billiard ball is made of zillions of atoms. And it tends to move at speeds that are much less than the speed of light. Billiard balls move much more slowly than this. Therefore, its motion falls into the regime of classical mechanics, and we can use Newton's laws of motion, Newton's theory of classical mechanics, to study how a billiard ball works. But if we look at much smaller scales, on the nanoscopic scale, where we're talking about individual little atoms, how small is that? Atoms range in size from about 0.03 nanometers to 0.3 nanometers. A nanometer is 10 to the minus 9th meters. So that's why we call this the nanoscale. When we're talking about systems that are the size of individual little atoms, or parts of atoms interacting with each other. On that scale, classical mechanics of Newton no longer applies. His equations, his laws, his theory doesn't make the correct predictions on these tiny scales. So we have another theory called quantum mechanics that started to be developed around the year 1900. One of the original innovators was a German physicist named Max Planck. In quantum mechanics, space and time still behave more or less the way that we're used to. You got time and space being separate from each other. But on those tiny scales, objects don't behave like billiard balls anymore. An individual electron instead behaves somewhat like a wave and somewhat like a particle. We call it wave-particle duality. Totally contradictory to our normal common sense. So this is the regime of quantum mechanics, things that are very small moving slowly. Now, if we move up here back to the macroscopic scale, and we take our billiard ball and we launch it at near the speed of light, so at very high speeds, then we enter what we call the relativistic regime, as described by Albert Einstein, a German-born Jewish physicist, in the year 1905. So the theory of special relativity describes large objects moving very fast at speeds near the speed of light. And strange things happen when you move at these relativistic speeds. Objects start to contract and clocks run at different rates for different objects, and space and time, instead of being separate things, get all intertwined and mixed up and wrapped around each other. They bend into each other. Time starts behaving like space, and space starts behaving like time. Totally different set of rules, a different theory of motion here. And then, if you take objects moving at that speed, but look at very tiny ones, so if you look at little molecules, or electrons, moving at near the speed of light, then we're in this regime, the regime of quantum field theory, as first developed by an English physicist named Paul Dirac in 1927. Again, if you're moving at relativistic speeds, space and time get blurred together, and as for what particles look like, I don't know how to draw that. It gets pretty bizarre. Not to worry, however, we are going to be focusing here on out on classical mechanics, the classical regime. Large things, macro scale things like chickens and billiard balls made of zillions of atoms moving relatively slowly at speeds much less than the speed of light.